Greetings, sir. My name is Akash Srikanth and my roll number is 21BCE1931. Today, I am doing the assignment on the NAND2TETRIS project 1, which is about gates. So, let's start with AND gate. So, first, let's see what is an AND gate. An AND gate is a basic digital logic gate which implements logical conjunction from mathematical logic. Basically, works like a multiplication. A high output 1 results only if all the inputs to the gate are high. If one of the inputs is also low, the function is low. Let's see this example in the NAND2TETRIS software. We first load the chip and then we have to load the script for the NAND and. Here we have written saying that if output is equal to 1, if A and B both are 1, if one of them is 0, the output is 0. We run this software, we run the program. After running, we change the select view to output. Here, from here, you can see that this is a truth table for AND gate, and this is the output we have got. When the inputs are low, which is 0, the output will also be 0. But when both the inputs are high, the output will be high. This is the first gate, which is AND gate. Now, let's see for the AND 16-bit gate. Logic. We run this code. Here, every single bit is compared to the every single bit of two inputs, A and B, are compared. If both are 0, then the output bit is 0. If both are 1, the output bit is 1. If 1 is 0, 1, the output bit is 0. Here, from the output screen, we can see that each, let's take this example, where every single bit is compared. It's 1 and 0. What does 1 and 0 give us? It's 0. The output bit is 0. Likewise, it goes. But for this, for an example, 1 and 1, the output bit is also 1. So each bit is individually calculated. Next, we look at demultiplexer. A demultiplexer performs the opposite of multiplexer. It takes in one input and gives a lot of outputs. Let's see the example for demultiplexer. We load the chip, demux. And we run the program. When we set the output to this thing, output value, we can see, let's see the truth table for demux. Sorry for the weird positioning. We can see that the select is 0, 1, and 0, 1. We can see input is when the input and select are both 0, 0, the outputs are both 0, 0. We can see when one of the, we can see when the input is, select is 0 and the input is 1, select is 0 and the input is 1, the value of A is 1, Y1 is 1. So from this, we can compare and see how a demux works on this software. Likewise, for a demux 4-way. 4-way demux means that there are 2 inputs and there are 4 outputs. Let me load the script. And let me run the program. After the program is run, so we can see that there are 2 select values. Select values can change depending on the program. So you can see that this is the output for mux 4-way, and likewise we have mux 8-way as well. Demux 8-way, sorry. For the demux 8-way, let me load the script. And I'm running the program. And I might have forgotten to tell, if there is any error, it will get displayed here, down here. Uh, let this program complete and I can explain that. End of script, comparison ended successfully. This means that there is no error there. And when I change the output to the output screen, we can see that there are three select inputs. And for the combinations, that's 2 power 3 combinations. And these are the outputs. So 1, 2, 3, 4, 5, 6, 7, 8. There are 8 outputs with one input. This is what for demux. Let's look at multiplexer. Multiplexer is a combinational circuit that has two input lines and one single output. For demux, we have seen that there's one input and two outputs. In mults, there are multiple inputs and only one output. This binary information is received from the output lines and directed to input lines and directed to the output line. On the basis of the values of the selection lines, one of the data inputs will be connected to the output. Let's look for mux in that in this software. We'll do mux. And let me load the script also. And let me run the program. Here we can see that according to the program, the value of A and B keeps changing. Now let me change the value output. So here we can see A, B are the input lines. S select, S means select, and out are the output lines. We can see that when it's 0, 0, it's 0, 0. And when input lines are 0 with the select 1, output is still 0. When the input, one of the input and one of the select is 1, both are 1, the output is 1. We can successfully see that both these two tables are in fact correct. So this proves that we have seen for mux. Let's see for mux 16. And let me run this program. We can see that the value keeps on changing here, input pins, and this is the output pin, one output pin. So this doesn't, this is just 16 bits for the mux. It's the same as this. So as usual, each single bit is individually compared, and then according to the select, an output is given. For example, this 0 and this 0 is compared individually. Then that value of 0 is put here. 0, 0 gives 0 output. With select 1, it gives 0 output. But in this case, we can see that A is 1 and B is 0 with select 0. Yeah. So this is for mux 16 bits. Now let's look at 4:16 mux, which means there are 4 inputs and 16. No, wait, 1 second. Yeah, there are 16 inputs and 4 outputs types. Let me load the script. There are 16 inputs and 4 outputs for this program. And let me run the program. See, output A if select 0, 0, B select 0, 1. This is how it works. Let's see this output screen. We can see that there are 4 inputs. There are 4, sorry. Yeah, 4 inputs A, B, C, D. As usual, each bit is individually compared and then the output is shown. For full view, let me do this. Okay, I'm sorry, there's some bug with the software. I'm really sorry. Let's go for the other one, which is mux 8-way, 8-way 16. And let me load the script for that one. And I'm running the program. See, there are 8 inputs. Let me show you the output screen. Uh, Unfortunately, I'm not able to turn left or right, but as usual, each bit is individually compared A, B, C, D, E, F, G, H, and then the output is shown accordingly. Now, let's look at another gate, NOT. But before going into this, we have to first see what is a NOT gate. So from this, a NOT gate, what is a NOT gate? A NOT gate is a logic gate that inverts the data input signal. A NOT gate always has high output when the input is low. Basically, if the input A is 0, then the output is 1. And if A is 1, the output is 0. It's basically output is equal to inverse of input. Now, let's see in this program. When I run this program, it says set in 0. When it's 0, the output is 1. Sorry. Sorry. Yeah. We see an output that when the input is 0, output is 1. It's inverse. When the input is 1, the output is 0. Now, let's look at this 16-bit NOT gate as well. We will load the script also. Sorry. We run this code. There are 16 bits in this program. I'll go for the output. So basically, where each bit is individually compared. So wherever there is 0, output will be 1. And wherever input is 0, output will be 1. Wherever input is 1, the output will be 0. 1, 0, 0 for 1, 0 for 1, 1. So that's how it goes. Now, let's go for the other gate, OR. OR gate is mostly used as digital logic circuit. The output state is basically like adding two inputs. Simply, if input value is 1, if any input value in the OR gate is set to 1, then it will always return high output value. So basically, it says 0, 0. There's no thing. So 0. 0 plus 1 is how I remember it. It's 1. 1 plus 0, it's also 1. And 1 plus 1 has output 1. Because if there is any high value, then the output is 1 for OR gate. Now let's check this in this software. We'll go for OR gate. Let me load the script for this one. See, it basically says output is 1 if A and B is equal to 1, or A is equal to 1, or B is equal to 1. Let's view this output. In this output, we can say that when any of the inputs is high value, 1, the output will always become 1. Here we can see that both are matching. This successfully proves that this program is right. And let's look at for OR 16 bits, sorry. Let me run this program. The output, we can see that as usual for every single 16-bit, each bit is individually compared. So for example, there is 0, 1. We know that if there is a high value, the output will become 1. So if any of these have 1, the output will be 1. If both of them are 0, the output will be 0. We now look at OR 8-way. Let me run this program and I'll explain it. I'll go to the output. See that when the input is entirely zeros, the output is 0. When the input has 1 anywhere, the output is 1. When the input has 1, there are 3 zeros, 1 followed by 4 zeros, but still the output is 1 because that input contains 1. If there is, it basically said if any input value in the OR gate is set to 1, the output will be 1. So now moving on, we'll go to the last chip in this project, which is XOR. I'll explain what an XOR chip is in a second. First of all, an XOR gate. An XOR gate is a digital circuit that gives a true 1 or high value when the input of a true or input of a number is odd. So basically, it says that 0 and 0 is 0, plus 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is not, it's not an odd value. So the output is 0. Let's check this in this program. We go to the output screen and we check that when A and B are both 0, the output is 0. When A is 0 and B is 1, the output is 1. When A is 1 and B is 0, the output is still 1. When both are 1, the output is 0. From this, we can verify that this code perfectly runs, and this is the same as the truth table for XOR gate. Thank you, sir. Thank you for this opportunity. Thank you.